So in the previous video, we went through the bits and pieces that we need to make a pipelined machine. I want to start with a summary of each of these incremental additions so that you have an idea of how to add to this pipeline, and then do a couple little tweaks to make it actually a little bit more functionally useful. So first of all, we start with our basic 3 stages, which is fetch, read, and execute. That I think is fairly straightforward, right? Because we're fetching into the instruction register. And then the only difference from our single cycle machine is that we add these latches on either side of the ALU, source and result. Then we add additional logic to calculate our, to do write back, as well as to show the following along of control information. That looks like this, right? We added some write back and we added control forwarding. Then we added branch calculation, and we also added the literals, right? We added the literal operation here. Where is that? Right here. Literal operations right here. And we added a calculation of a new program counter for our branches. And then finally, we added some data, which allowed us to use the output of the ALU to produce an address for the data memory that then can be used to load or store information. So that's our full machine. Now, a couple little tweaks that we're going to do. If you notice here, what I've done is I've actually moved the literal to the bottom of the ALU instead of the top. So the first one, if we go back one slide, you can see we've got all of these options at the A input of the ALU, and the B input of the ALU is just a register. Now, some machines will do this, right? To say you've always got a register, it's a register plus something, right? Register plus the program counter, register plus a literal, register plus a register, and that's fine. But in reality, we're going to find that if we want to do offsets from the program counter in order to do a branch, the assembler knows that value in advance, and so it's better to put that as a literal. And then that's that tweak. So we want to be able to add the program counter to a literal value, and so we just move that to a different multiplexer. And this is the kind of thing you do when you're developing these chunks of hardware, is you look at what they're doing, and then you walk through the operation of an instruction, and you notice, oh wait, that's going to be a problem, so we got to make a little tweak here, make a little tweak there. The other thing we add here is a condition code register. Condition code register. Well, this is a register that stores information about the result of the ALU as opposed to the result itself, right? This R value is the result of the ALU, but this CCR, the condition code register, allows us to collect and then move along information about that result, right? Was it a 0? Was it negative? Was it NZVC? Was it negative? Was it 0? Did it have overflow, and was there carry, right? These are the sort of 4 typical flags that we use to give us some metadata about the ALU result. And in some cases, it's going to be useful to collect that and sort of move it along. So that's why we do that there. So that's our full machine that we're going to be using. And I'm sorry that I'm still sort of covering the little bit of the data memory there, but there's nothing there that you need. So let's see how this works. Let's trace the execution of a makeshift instruction. So this is the sort of fake assembly language that Clements proposes. Again, this is the Alan Clements textbook. And in a different video that sort of builds out the RISC-V pipeline, I do this with real RISC instructions. But this is close enough. What this does is it loads into a register D the value that's in memory at the address calculated by register S1 plus the literal L. And this is a kind of register indirect addressing where you calculate an address and then you use that to access memory, and then you use the memory to get you some data. So let's see how that goes in this pipeline. Step 1 is fetch. This is the only hardware that is used for this instruction at fetch. The rest of the pipeline will be doing other things to other instructions. Once this is done, we've used the program counter to address the instruction memory and got the instruction into the instruction register. Then the clock ticks and everything shifts. Now, in the second clock cycle of this instruction, The instruction register contains the information about which registers to use and what information, what's the literal value, what's the destination, what's the opcode, what are we doing and where. The register file is consulted and the result is placed into this intermediate latch between read and execute, right? This is the ALU source latch again. And again, something else is being fetched. Something else is being executed. But for this instruction lives here and nowhere else. Once that's done, the clock ticks and everything shifts down by 1. Now, this instruction is at the execute phase. Now, for a load instruction, the execute phase is going to be calculating the effective address. So we're going to take the literal value that we got from the instruction register here, and we carried it along. Now it's here. We're going to take that literal value, sign extended of course, and present it to one input of the ALU. And then we're going to take the other source register here that we got from the register file last cycle and present it to the ALU here. Now here we have choices, right? Those multiplexers have to be controlled. And so the control logic in the pipeline is going to take the information from the opcode saying what it is we're doing, use that information to activate those multiplexers, ALU A and ALU B, and choose the inputs that are presented to the ALU. But that's the only choice to make besides what we're doing, right? The opcode tells the ALU directly what it's going to do. Maybe there's some logic required, but basically it does. And then we make these choices with this multiplexer. And then once that's done, and again, something else is being fetched, something else is being read from the register file, and memory is being used by some other instruction. Once this is done, the clock ticks, and then we do the memory access or write back, right? This is the 4th stage, memory access or write back. Depending on what the instruction is, memory may or may not be accessed, right? The register file may or may not be written back to, but those are the things that could be done in this stage of the pipeline. So here, what we do is we take the destination address, which we've been just holding in our back pocket the whole time. We don't need the destination address here or here, but we do need it here. So now that we've collected it, we've kept it with us, we're going to present it to the data, the write back address of the register file. This is where to put this result. What's the result? Well, in this case, because we're loading, right, load instruction, the ALU result here is the address for memory, and then memory gets accessed, and then the result gets used as the value that gets written back into the register file. And again, there's a choice to make, right? This multiplexer here makes a choice between whether we're taking the ALU result or the memory result and storing it back in the register file. And so the opcode, which again was collected along here, oh, I wonder if that's a mistake. Maybe we need the opcode still because we need to tell the machine whether we're actually writing back or not, what we're doing here. Yeah, we may need a bit more information. What we're doing should be collected each cycle so that we can make these kind of choices. Then the result from memory is written back into the register file and we're done. So that's the full trace of an example instruction. And we could do different instructions if we wanted to do different things, but that gives you an idea of which parts of this pipeline data path are used at each segment.